this lesson is about calculating the Ka and the pH of weak acids. And you're going to want to print off or have access to Appendix D, which is our aqueous equilibrium constants. And this is a helpful tool that you're going to want to have at your fingertips while we're going through this. You're also going to want your calculator out and handy. So recall from our previous lesson that the word strong means 100% disassociates, and there is no equilibrium that sets up. However, a weak acid does not disassociate in water completely, and when I think about the term weak, I think equilibrium. So setting up between the conjugate pairs is an equilibrium problem through and through. So we need to set up our values for hydrogen ion concentrations from an ice chart. So because a weak acid does not disassociate in water completely, when I think about the term weak, I think equilibrium. Setting up between the conjugate pairs is an equilibrium problem. So in this case, I have a weak acid combining with water, and we see that these double arrows is telling me that it is in equilibrium with H3O+, our hydronium ion, and A negative, showing our conjugate base for our acid. So to set up this equilibrium constant, we're going to use a generic KEQ like we did with the last chapter, knowing that this is going to turn into Ka for our equilibrium constant for an acid. And we're going to show this as doing our products over our reactants. So the concentration of our H3O+ times the concentration of our A-, which is the negative conjugate base, set over the molecular form of our acid, HA. And remember that pure solids and pure liquids drop out of the equilibrium value, so that water just gets dropped out. And we have our product ions over our molecule reactants. So here we have our Ka, which is our acid dissociation constant. Every weak acid has its own unique value for an acid dissociation, and we recognize that's the magnitude of the number that we find interesting. Our Appendix D lists for us alphabetically some of our more common acids, like acetic acid, and we can see our acetic acid is HC2H3O2, and then it has a Ka value of 1.8 times 10 to the negative 5. So it's pretty small, indicating that acetic acid is a very weak acid. Compare that to some other acid, arsenious acid. And here we have different triprotic acids, so we can see each of the ionizable protons. So we can say the larger the Ka value, the stronger the acid is. And remember, there's no units to our K constant. It's the magnitude of the number that we find interesting as a chemist. So our Appendix D gives us the listings at 25 degrees Celsius. And again, the magnitude of the Ka tells us how strong or weak our ionizing proton is. Now remember, weak acids set up equilibrium. So when I refer to how strong or how weak, I'm referring to how weak a weak acid is, or how strong a weak acid is. Remember, we have our 7 strong acids. Our 7 strong acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, perchloric acid, sulfuric acid. These 7 are strong acids. There is no Kas for these because they 100% disassociate. There is no equilibrium for these 7. So when we talk about stronger Kas versus weaker Kas, when we look at this appendix, they're still all for the weak acid. So let's just say those one more time, hopefully to get that stuck in your head. Hydrochloric, hydrobromic, hydroiodic, nitric acid, chloric acid, perchloric acid, and sulfuric acid. Those 7 do not have a Ka value. You will not find that in that Appendix D because those acids 100% dissociate. They do not form an equilibrium. So everybody else will have a Ka value. That doesn't mean that they're all created equal though. The larger the value of the Ka, the stronger the weak acid. Again, so we can have a strong weak acid. It's still not strong like our top 7 strong. It's favoring the product side of our equilibrium if it has a larger Ka value. The larger the number, the more we produce product. Smaller the number, the more we favor the molecular form. We're going to be asked to calculate Ka from pH or pH from Ka problems. And as we begin to do that, we know that Kas are very small numbers and that they're favoring the molecular form of our organic or our inorganic acid. So if Ka is small, we always begin by writing the major species And what I mean by that is figure out what the chemistry is. What are the reactants and what are the products? And begin to write about them and determine what acid am I going to be looking up for my Ka chart. It always starts with an equilibrium problem right from the start where we're trying to determine the hydrogen ion to find the pH of the system. And then we can compare Kas to Kws to determine if a solution will end up to be acidic. Now let's put this into an example. So here we have a student prepared a 0.1 molar solution of formic acid and measured its pH using a pH meter at equilibrium and found it to be 2.38. So calculate the Ka for formic acid. So again, we always want to start by writing out our chemistry. What is happening? Well, I'm starting with formic acid. HCHO2. And what's happening here, when we add this into water, it's going to dissociate. So we're going to have our H plus, and so this is our ionizing acidic hydrogen. So the H plus comes off, and then we're left with CHO2 minus. Now formic acid, it came from 8. So this is the formate polyatomic ion. All right, so then we can set up our ice table. All right, let's look at this. We were told that initially I had 0.1 molar solution of my formic acid. 10 molar of that. And I did not have any of my product. We're just going to draw our little grid chart here. And then we were told at equilibrium, where pH was 2.38. Well, if we know that our pH was 2.38, we can find our hydrogen ion concentration, remember, by doing 10 to the negative 2.38. And if we take our calculator here and do 10 to the negative 2.38, we get a hydrogen concentration of 0.0042 molar. All right, so let's plug that in here at equilibrium, 0.0042. Now, we know that we have a 1-to-1 ratio here. So I also have my anion here of 0.0042 M. We can also see that this change here was going from 0. We had to add 0.0042 plus 0.0042. And then we also can tell this that might change since, again, a 1-to-1 ratio, that we lost 0.0042 from my initial formic acid. So then we just need to subtract 0.1 minus 0.0042. So at equilibrium, my formic acid's concentration is 0.0958. Okay, so now that we know all of my equilibrium values, I can set up my Ka. So again, we have products over reactants. So 0.0042 times 0.0042, we can write as 0.0042 squared. Again, all we did though was H plus times our CHO2 minus 0.0042 times 0.0042 divided by the concentration of my formic acid, which is 0.0958. And so my Ka is equal to, let's set this up, 0.0042 times 0.0042 divided by 0.0958. And I should get 1.84 times 10 to the negative fourth. 1.84 times 10 to the negative fourth. Again, there's no units when we are finding our equilibrium constant. So to review, let's see what we did here. We were given initially the concentration of my formic acid. We were also given its pH at equilibrium to be 2.38. We were able to take that 2.38 and find the hydrogen ion concentration at equilibrium. And with that, we know that because we have a 1-to-1 ratio, we know the concentration of our anion. And in order to find that concentration, remember we just took our pH and we did 10 to the negative pH to get that hydrogen ion concentration. So once we know the hydrogen ion concentration and our formate ion concentration, we know how much it took to go from 0 to that by that change. And again, because of a 1-to-1 ratio, we know how much we lost of our initial concentration of the formic acid. So when we subtracted those two, we got how much remained at equilibrium. Then we were able to do products over reactants. Ions, our ion products over our molecular starting point, or dissociated over our non-dissociated to find our Ka. So let's figure out what percentage of the acid ionized in this solution. So what we're going to do is we're going to take the amount of acid that we changed by, or how much H plus was created, 0.0042, over our initial 0.10 molar, and then times this by 100. So when I plug that into my calculator, 0.0042 divided by 0.1, and then times it by 100, I got 4.2%. And if we were to write this in like a generalized format, we could take our H, or our percent ionized, is equal to our H plus concentration over the concentration of our initial, we'll just use our generic HA for our initial acid. And then times that by 100. So that's a pretty small percent. So really, when we look back at this equilibrium, that means only 4.2% have ionized. So a really small arrow to the right and a really big arrow to the left. So our equilibrium is definitely lying to the left in this case. Now, if Ka is quite small, it's okay to make some assumptions. If Ka is small, the equilibrium lies far to the left, and the initial concentration of the acid will be essentially the same number at equilibrium. So what this is telling us, if the equilibrium lies far to the left, that's telling us that it's favoring the molecular form of the acid. It's favoring the reactants. And if we look back at this, we can see that our initial is 0.1 molar, and at equilibrium, 0.0958. I mean, this is really, really close to this number, right? So we had a very small difference from our initial to equilibrium. So essentially what we're able to do is we're eliminating the need for the quadratic equation. So there's this 5% rule that chemists use. When we find the percent ionization to check our assumption, a general rule is that quantity of X meaning how much we're losing here, is more than 5%, then you'd better use the quadratic formula. And you wouldn't have to do, if it's less than 5%, you do not need to use your ice chart. So let's just say, for example, so if we were to plug in our values for Ka using our 0.0042 squared, but instead of using this equilibrium value, taking out this minuscule amount from our original acid, if we used our original amount of acid, 0.10, and we did this math, we would get 0.0042 squared divided by 0.1. And our answer would be 1.76 times 10 to the negative fourth, which is really similar to what we got. 1.84 times 10 to the negative fourth, 1.76 times 10 to the negative fourth. So we're underneath of that 5% rule, which is acceptable for doing when we have such a small difference in Ka. So if it's less than 5%, we can assume that you can use that initial value. But if it's more than that, then we need to work it out with our ice chart. Let's look at another example here. Niacin, one of the B vitamins, has the following molecular structure. So niacin is part of an aromatic ring, six-sided ring, aromatic, so it has alternating double bonds with a nitrogen. And off one side of the aromatic ring is our COOH, our COO, which is an organic structure here. And this H is our acidic or ionizable hydrogen. So this is part of our monoprotic acid right here, which is what's going to ionize. So let's say that I have 0.2 molar solution niacin has a pH of 3.26. What percent of the acid is ionized in this solution, and what is the Ka for it? So let's say that our niacin, we're just going to abbreviate and we're going to say HA. And we have some sort of an equilibrium here. We'll see which direction it's favoring. And we have our H plus, and then with this H that's being broken off, that's acidified, and our A minus, which is the rest of our niacin that's being left behind. So let's set up our ice chart here. And we know that initially we're told that we have 0.2 moles per liter of niacin. And of course I have no of my products yet, no products. And I have a pH of 3.26. So we can find my H plus concentration by 10, and this is at equilibrium, 10 to the negative 3.26. So let's do that on a calculator here. 10 to the negative 3.26 is 5.5 times 10 to the negative fourth. So our H plus is equal to 5.5 times 10 to the negative fourth molar. So I'm going to put that in here at my equilibrium, 5.5 times 10 to the negative fourth. And again, we have a 1-to-1 ratio here, so that's the same amount as my A minus here, my base. So let's see, before we finish filling in the rest of our ice chart, let's figure out that percent that's ionized. And I'm going to slide this over here, and we know that to find our percent ionized, we do the change, which we know in order to get from here to here, we added 5.5 times 10 to the negative fourth. So that means that we're subtracting, that's our change of our original amount of our acid. So let's do our 5.5 times 10 to the negative fourth divided by the initial amount of acid I started with, 0.2. And these are all molar concentrations. So let's do that 5.5 times 10 to the negative fourth and divide it by 0.2. And then, of course, we're going to times it by 100. And wow, we got less than a percent, 0.275%. Okay, so that's way less than our 5% rule. So we can just skip all of this. It's so negligible, the change of my acid, that we can just plug in for our Ka, our products, so 5.5 times 10 to the negative fourth, squared, right, because this times this, divided by, and now instead of using the new equilibrium constant that's so negligible, it's less than 0.5%. It's almost 1/4%. We can use our 0.2 molar initial concentration because that change was so negligible. Again, that 5% rule is an understanding that chemists use. So let's figure out what this Ka is. And we'll do 5.5 times 10 to the negative fourth squared divided by 0.2. And I got 1.51 times 10 to the negative 6. 1.51 times 10 to the negative 6. And again, this is a pretty small number, showing that the equilibrium is laying far to the left. So again, we were able to determine that the difference, well, using our equilibrium values that we found by doing, taking the pH and doing 10 to the negative pH. So we have our products, and we were able to then take that number, which is our change, divided by original value of our acid, to find that we were way less than 5%. So we could throw out the ice chart. And to find our Ka value, we'll do our products divided by, instead of using the equilibrium reactant, since that change would be so negligible, we can use our initial concentration that we were given to find our Ka for niacin. So we've been using pH to find Ka. Now let's use Ka to find pH. So we're still going to write our equilibrium. We're going to write our equilibrium constant expression, find the concentrations that are involved using our ice chart, and then substitute values in. So let's look at an example. We need to find the pH of a 0.2 molar solution of HCN. The value found in Appendix D for the Ka of HCN is 4.9 times 10 to the negative 10th. And just pulling up this chart here just to kind of show you the hydrocyanic acid, HCN. Its Ka value is 4.9 times 10 to the negative 10th. So this is a given. All right, so now let's write our expression first. So I'm going to write out HCN is in equilibrium with our H plus and our Cn minus. So let's make our ice chart. Our initial, we were told, is 0.20 molar. And we know we don't have any of our products yet. We know that we are going to lose reactant, and we're going to gain product. And we know that this is all a 1-to-1 ratio. So that at equilibrium, our H and our Cn are going to be X. And at equilibrium, we're going to be 0.2 minus X. So let's look at our Ka expression. Our Ka is equal to our product, so H times Cn, concentration of H, times Cn, all over HCN, which we know is equal to 4.9 times 10 to the negative 10th. Okay, so we know that H and Cn are X, so X times X, so we can just say X squared over. Now let's look at this product. Remember that 5% rule? We're going to assume, we're going to make an assumption here. We might have to back the bus up if our assumption is wrong. But let's make the assumption that we're under 5%, and let's use our original concentration. If we're wrong, we can go back and we'll have to use our quadratic formula to use our 20 minus, or 0.20 minus X. But let's make that assumption first, and then we can go back and check. So X squared over our initial concentration of 0.20, and then set that equal to 4.9 times 10 to the 10th, negative 10th. And let's solve for X. So I need to do 4.9 times 10 to the negative 10th times, so we're going to cross multiply here, times 0.2. And I have equal to X squared, so I need to take the square root of X to get just X. So square root of my answer. To get, let's 9.9 times 10 to the negative 6. So X is equal to 9.9 times 10 to the negative 6. And this, we know X is, so that is equal to our hydronium, our H plus concentration. Now let's do a quick check to see what percent that would be. So we know that our change, right, our X is equal to 9.9 times 10 to the negative 6. So let's do 9.9 times 10 to the negative 6 over our initial 0.2. Let's see what we get here, and then times it by 100 to find out what percent we are. So I'm going to divide that by 0.2, and we're going to times that by 100, and we get, wow, we're 0.005%. 0.005%. We are well within under our 5% rule. So we can just cross off this whole middle part of this ice table part. We can just assume that that change was so negligible it didn't even touch our initial concentration. So we're not done yet. We do have our H plus concentration. We need to find our pH. So remember, to find our pH, we're going to do the negative log of our hydrogen concentration. So the negative log of 9.9 times 10 to the negative 6, negative log 9.9 times 10 to the negative 6, did I write that right? Is equal to, we have a pH of 5.00. Again, we want 2 decimal places. Our pH It's 5.00. Let's use Ka to calculate percent ionization. So we need to calculate the percentage of hydrofluoric acid molecules. It's ionized in a 0.1 molar HF solution. So let's write down HF in equilibrium with H plus and F minus. And let's look up on our appendix to find hydrofluoric acid. So we have hydrofluoric acid, HF, and its Ka would be 6.8 times 10 to the negative 4. So let's write that down. Ka, 6.8 times 10 to the negative 4. So when we write this out, and we're told that our initial concentration is 0.1, so we know that these are 0, and that we're going to gain X, so plus X plus X. So when we set this up, we can say that our Ka is equal to our X squared over, again, let's make the assumption, the 5% rule, over 0.1. And then we'll set that equal to 6.8 times 10 to the negative 4th. So let's solve for X in this case. So I'm going to do 6.8 times 10 to the negative 4th times 0.1, and then take the square root of that to find X, which is 0.0082. And then again, remember, to find our percent, we're going to take that change. We know that our change is X. So we'll do 0.0082 divided by our initial 0.1, and then times it by 100 to find the percent ionization. So 0.0082 divided by 0.1, times it by 100. And, oh, we got 8.2% ionized, which is greater than 5. So we would need to go back. If we were asked to find more information about this, we would need to go back and set up that ice chart. This just wanted the percentage ionized. So we would need to go back and set up that ice chart because it is greater than 5%. Now let's look and see what happens when we dilute this. If we diluted and went from 0.1 molar to 0.01 molar, let's see what that does. So again, we know our initial of 0.01. And again, we still know 0, 0 here. We're still changing by X. So we can set up our same setup. We can say our Ka was 6.8 times 10 to the negative 4th is equal to X squared over 0.01. And let's see what that gets us. 6.8 times 10 to the negative 4th times 0.01, and then take the square root of that, we would get 0.0026 molar for our H plus. And again, if we take that 8, or the X, and divide it by 0.01, which was our initial concentration, times it by 100, to see that percent, we would do divided by 0.01 and times it by 100. Holy smokes, we have 26% ionized. Which is substantially more than that 5% rule. So by diluting it with water, it's causing it to ionize substantially more. And so we can see here down in our notes that by diluting the solution by a factor of 10, the percentage increases by almost a factor of 3, actually a little bit more, going from 8 to 26. This one was 8%, 8.2, and this was 26, so 8, 16, 24, a little bit more. And this is in accordance, if you think about it, it's really an example of Le Chatelier's. There's more particles on the right side of the equation than on the left. Dilution causes the reaction to shift in the direction of the ions or particles, or we can see that it's shifting to the right because it's countering the effect of the decreasing concentration of the particles. So we're decreasing on the left, so we need to increase on the right. So let's look at a problem that we did earlier where we found the percent ionization of niacin in a 0.2 molar solution. And we actually, this is incorrect, it was 0.27%. 0.27%. Let's calculate the percentage of niacin when the solution is diluted from 0.02 to 0.01. All right, so we're given the Ka for niacin is 1.5 times 10 to the negative fifth. And remember, we would do our products over, so our x squared over, let's do our initial concentration of 0.01. And let's solve for x here. Let's do our 1.5 times 10 to the negative fifth, times that by 0.01. And then to take the square root of the answer, we would get x of 3.87 times 10 to the negative fourth. And remember, that's our H plus concentration at equilibrium. So let's find the percent since we know x and we know our initial concentration. So we would do 3.87 times 10 to the negative fourth divided by 0.01 and then times that by 100. And we get 3.87%. That's ionized. So we are under the 5% rule still. We can make that assumption that the change was very negligible. However, we can see that the percent went up, right? When we diluted the solution, we went from 0.27 to almost 4% of the niacin molecules that are ionized. Now let's try diluting it even more to 1 times 10 to the negative 3. So that if we wrote that out, let's see, 0.001 molar, that would be 1 times 10 to the negative 3. So let's try writing that out. Same, where we would do our same Ka value times 10 to the negative fifth is equal to x squared over 0.001. And we would find that x is equal to 1.5 times 10 to the negative fifth times 0.001. And then we need to square root that. So our x is 1.22 times 10 to the negative fourth molar. And again, that's our H, concentration of our H plus at equilibrium. So if we were to take this x, that change in concentration, x divided by our initial, so let's take this and divide it by 0.001 and times it by 100. We get 12.25% ionized. Notice that difference just by changing by a factor of 10 dilution. So by doing this, if I wanted to find the pH of my H in the solution, I gotta figure out if I'm below the 5%. In this case, I can just use the easy math, do the same thing, and I can do the negative log of my 3.87 times 10 to the negative fourth to find the pH of the solution. However, in this case, since I'm above 5%, I'm at 12.25, I gotta back the bus up, I have to do my ice chart in order to solve for x, in order to do my negative log of x to find the pH, because the difference is not as negligible, so we need to have that equilibrium set up. And this is just also another example of showing Le Chatelier's principle. If I have my niacin, I'm going to turn my paper sideways here so we can see. If I have my niacin, spell right, Niacin, niacin, and I'm putting it in water. Obviously, I'm putting it in more water to dilute it. So it's going to be in equilibrium with my, we'll just call this my HA. That'll make it easier. My acid plus water. And it's going to give me my H plus, and I guess I don't need brackets for that, huh? My H plus and my A minus. So if I increase my water, it's going to push my equilibrium further to the right and increase my products being formed. And so we can see that the percent being ionized is going to be even greater. So we're just really showing that. Also make sure that we find this percent, and if it's below 5, we can just continue finding our pH as normal. If it's greater than 5, we need to go back, do the ice chart, and